Our next speaker is Noam Tal. He's algorithm manager at Applied Materials. Noam holds BSc and MSc in physics with research in the field of superconductivity. Noam has vast experience in the semiconductor industry in leading companies like Intel, Nova, and Applied Materials. Noam is leading an algorithm group developing deep learning solution for next generation anomaly detection and segmentation industry-specific solution. He will talk about generating the perfect reference, anomaly detection via fusion of stochastic and deterministic learning.
Thank you. Happy to be here. So generative models are doing amazing job today in vision, in language, but for some real-world applications, we want it to be very accurate. And accuracy sometimes contradicts with the idea of randomness in generative models. So how do we overcome that? I want to show you some of the challenges we have in applied materials in the domain of anomaly detection. So how accurate can we get? So we're going to see, but let's start with a short introduction. So we come from the semiconductor industry, and this is where we design and manufacture integrated circuit on a nanometric scale. And the outcome of it are the electrical components that we have in our electrical devices. So it all begins with a wafer, okay, a silicon wafer. This is how it looks. This is how it starts. And we build like billions of transistors on top of this silicon wafer, and it goes through a very long process that can take up to 6 months. And at the end of it, we have some these electrical components we call dies. We cut it into dies, and we have like hundreds of dies on a single silicon wafer. And in order to monitor this process, we need tools, we need machines which are very accurate at the nanometric scale. And for that, you need scanning electron microscope. It's a special microscope using electrons in order to get to this high resolution. So these are the kind of machine that we do that we manufacture in applied materials here in Israel. And what are we searching for? So these machines are scanning the wafers and looking for defects. Defects are pattern anomalies, pattern distortions, and stochastic particles. How do we usually track it? Traditionally, we just take a snapshot of the die and of the reference die, and we compare them. And sometimes it's very easy to see in comparison and to track the defect, but it becomes very much challenging when the defects are very small. So for instance, in this example, you see that the SNR of the residual image becomes very noisy. Can you see it? I'm not sure. So, and why is that? This is because not all dies created equal. And and we have process variation and imaging conditions that are different between the dies, and this is where it becomes challenging. So how about, instead of taking the reference image, which is not perfect, how about generating it ourselves? So we're taking pairs of defects and reference images, and we map it to each other, and we train a model. This model actually needs to do 3 tasks. So the first one is to learn the nominal distribution of the pattern and the nominal noise. And the second one is identify abnormality in the image. And the third is repair the defective area. And of course, by generating the images in a generative model, we can get a cutoff the machine production time by 2. So we can use any generative model to do that. And we started testing this idea with the MVTech data set. And so we took some images, some clean images. We implanted some anomalies, some distortions, and then we trained the model. And as you can see here, these are interchanging images of the defective image and the generated corrected image reference. But is it good enough for the semiconductor industry, for the anomaly detection in SEM? Well, you can guess that in the random process that we're having, every generation is somewhat different due to the noise that we have in the natural reference that we have. And so how do we overcome that? So one idea is use the well-known noise reduction techniques, any of the classical approaches of machine vision. But the question is, can we have a generation that is better than the random one? We want to see if we can utilize the model representation that we have in the generative model. So I want to show you here two approaches that we took. The first one is Monte Carlo sampling. So we're sampling the latent space. We're generating multiple inferences of the same image. And as you can see, the more we generate, the more instances we have of the same image, we can get a more consensus residual and get actually a better reference. If we go and walk through the latent manifold, we can optimize it and find the, I would say, the optimized point for the generation to have the perfect reference. But this requires optimization for each inference, so it does not come without a cost. Another approach that we took is during our research, we realized that our scheme is very good in training, in erasing defect. Okay, it tracks very good the defect and erases it pretty well. But the problem is that the normal area around the defect actually becomes noisy. It induces noise due to the nature of the natural reference. So what we actually want to do in the normal areas is reconstruct it the best as possible. Okay, we want it everywhere else to be exactly as the input image, but the defective area. So what does better this reconstruction task is actually autoencoder. So we proposed here to use an additional training mode that uses autoencoding from image to itself, and by that achieving a fine detailed reconstruction for the normal areas. And if we balance these two modes, we optimize these two training modes, then we can achieve better results. In order not to completely destroy the distribution that is learned, we actually shut off the randomness in the training while doing the training of the autoencoding mode, and it becomes a deterministic training mode. So the fusion takes us to a better result. We're getting better reference than all the other approaches that we took so far. And is it perfect? Well, we're getting there. That's it. I want to thank my partners to this journey, Boaz Turlesi, Yotam Ben Shoshan, and Nati Ophir. Thank you.